This is Ampere's law. Why should you care about Ampere's law? Because it gives you a shortcut to find the magnetic field created by a current. By shortcut, I mean you don't have to use the monstrous Biot-Savart law. But this will only be helpful if you have certain symmetries, and we'll talk about that in a minute and go over all those problems. First, let me just show you what this thing says. Ampere's law says that if you take the closed path integral along some closed loop, these are called Amperian loops. So I'm going to integrate B along some loop. You start at some point, you get all the way back to the same point. It does not have to be a circle. I drew this as a circle. You could take any path you want. Ampere's law will be true for any shaped path as long as it's closed up. That's what this circle here means. Well, along this path, you have to take the integral of B dot dl. dl is an infinitesimal line element of your path. So right here, dl is pointing that way because it points along the path. B, let's say, points that way. You'd take B dot dl. So you'd look at the theta between them. So you do magnitude of B, magnitude of dl times cosine of the theta between them. This would have a little positive contribution. They have components in the same direction. You look over here, dl and B happen to point the same direction. Here, B dot dl is going to be a big contribution over here because they're pointing the same way. Cosine of 0 is 1. And you get over to here, this point, let's just say B pointed perpendicular to the path at that moment. Well, this wouldn't contribute anything to this line integral because cosine of 90 is going to be 0. So if you do this, if you take this integral of B along the path all the way around, Ampere said that this integral is always going to have to equal mu naught, which is just a constant. It's 4 pi times 10 to the negative 7th. That this is going to always have to equal mu naught times the I enclosed. What do we mean by that? Well, this is a closed loop, so there might be current piercing the area defined by this loop. So this loop's going to define an area. If any current pierces that area, it's enclosed by the loop. And so I1 is enclosed by this loop. It's coming straight out at us. So I1 would have to go up here. You'd have I1 as part of your I enclosed. I2 is also going into the loop, but this one's going into instead of out of. So if we call out of positive, we'd have to do minus the magnitude of I2. I3 out here does not pierce this loop. So it does not contribute to the closed integral of B dot dl around this path. That doesn't mean it can't contribute to the magnetic field at these points, which sounds counterintuitive. How can it contribute to the magnetic field at these points but not contribute to this closed integral along the path? Well, because whatever contribution it makes here will get negated on the other side. So currents that are outside of this loop, they can make contributions to this, but any positive contributions will get negated further on in the loop. It's only currents that are inside of this loop who have net amounts of contribution to this closed integral of B dot dl. Okay, so you're probably thinking like, this doesn't sound like a shortcut at all. This sounds crazy complicated. Well, it does sound like that, but the only reason you'd use Ampere's law typically is if there's a nice amount of symmetry. A nice amount of symmetry that will let you bring B out of the integral. Why would you be able to do that? You pick an Amperian loop such that B is uniform along that path. This is the name of the game with Ampere's law. You pick the path so that B is uniform, because if B is uniform, it's constant with respect to that path. You bring it out of the integral, you just get B, and then integral of dl is just L. So this left-hand side typically does not give you any trouble with Ampere's law. Counterintuitively enough, it's the right-hand side that's the hardest part, and you'll see why in a minute. But if you're using Ampere's law, oftentimes you're just going to be using it in this fashion right here. You'll have B times some length. You know, if it's a circle, it's 2 pi r. That's the circumference. If it's a square, maybe it's 4 times L. Take B times some length. That's going to equal mu naught times I enclosed. And we should say that it's good to use the right-hand rule to find the directions. This is still going to be handy. So if you put your right thumb along the direction of the current, your fingers will wrap around in the direction of the magnetic field that's created by that current. So this is just something that helps out. Okay, let's look at the Ampere's law problems. Here's the easiest one, infinite straight wire. Now with the Biot-Savart law, this is nasty. There's like 6 lines, 7 lines. There's crazy integrals to do. With Ampere's law, this is like a 2-liner. Integral B dot dl equals mu naught I enclosed. Pick an Amperian loop. Well, we pick an Amperian loop such that B is uniform. That's easy. Just pick a circle centered at the wire. So this is a front view. If this wire is coming straight at us, the magnetic field is just going to be circling around here. If we're equidistant along our Amperian path, the B is the same at every single point, albeit from direction, but it's always going to be pointing in the direction of our Amperian loop. We bring our b out, integral of dl is just L, but the L here is just 2 pi r. The length of our Amperian path is just 2 pi r. So the left-hand side, no problem, b times 2 pi r. Look at the right-hand side. How much current is enclosed by this path? Well, the area defined by this path is going to be this here, and the current passes at one time, so we stick that one current there. You get b naught equals mu naught I over 2 pi r. When you solve, this is the most classic formula for the magnetic field from an infinite straight wire. With the Biot-Savart law, it's like 7-8 lines and it's nasty. With Ampere's law, it's just a straight gimme one timer right there. So that's the easiest one, infinite straight wire. What if you had a solenoid? A solenoid is you take a wire and you loop it around over and over and over and over and over. We're going to assume this is infinitely long. Are there infinite solenoids? No, but every single textbook's going to make you assume you've got an infinite solenoid, or at least that the size is big enough that this is going to be a good approximation. What shape do you make here? It's not obvious, but what you should do is make this rectangle that pierces straight through the middle, right through the guts of this solenoid, and then runs down it and goes back and goes around in some direction like this. The reason being, if you use your right hand rule, put your thumb in this direction up here and ask which way does the magnetic field go, the magnetic field is going to be pointing straight through here. So this is going to be the direction of the magnetic field within this solenoid. So if you stick your thumb along this path right here, you'll get your fingers curl around inside this way, and same here, and same here, and same here. And so you want your path down here to go right with the magnetic field. I don't want it like curving in here so I don't have to deal with any weird dot product changes. If B goes right along the path, then along this portion here of the Amperian loop, I just get B times L is the contribution. During this portion right here, I get no contribution to the path integral because the dot product is going to give me 0. B is perpendicular to the DL, and so I get nothing for that path. What about this over here? Well, we're going to say that that's 0. Why? Because it's an infinite solenoid, but those don't exist. I know, but every professor is going to have you assume it like that. They're going to say, oh, B is very small out here. Is it small? Yeah, it's typically very small. Is it 0? No, it's not 0, but you're going to pretend like it's 0 because that's what every textbook wants you to do. If you want to figure out what this is, join NASA. They literally have books on how to find exactly what the B is out here. It's a nasty calculation. It's kind of cool, kind of interesting if you're into it. But for our purposes, all that matters is this part right here. Everything else is a 0 contribution, either because it's perpendicular or because the B field out here is basically 0. So what do we get? Well, we just get B times one length, this length of this path right here, B times L. Mu naught, how many I's got enclosed? Well, let's check. If this is the area, if this surface right here is the closed area, how many times did the current pierce? It pierced it a lot of times. Check it out. So it pierced it once and twice and thrice and 4 times and 5 times. It pierced it however many n times there were in that little length. So if we divide this side here, we got n times the current because this time our area got pierced n times. How many? Well, you'll see in a minute. Let's just divide by L. And we get this mu naught n over L, which is the characteristic turns per length of the solenoid. So this little n is what we use to represent the turns per length. Typically, this is just a constant value. You get the same turns per length. And this is how you buy a solenoid. If you looked in a catalog, they'd be like, oh, it's 1,000 turns per meter or 20,000 turns per meter, and this would tell you what the little n is, and that's what capital N per L is. So that just depends on how long you make this Amperian loop, but if you make it longer, you'll get more loops, and it's always this factor of turns per length for that solenoid. So that's a solenoid. That's another classic example of using Ampere's law. The toroid or the torus is another example. Let's say you took a solenoid, but you kind of bent it into a circle. So you bend it into a donut, and these red lines here are windings of current that you've wound around and around and around and around, and you got this donut shape right here. So what do we do now? Well, this time we are going to actually just make a circle within the torus, and this is going to be our Amperian loop right here. So we're going to go around this ways. So imagine turning this 180 degrees or 90 degrees, and you'd have this right here. So your 2 pi r is the length of your path. So I'm going to bring the B out. B is going to be uniform in here because it's symmetrical. You know, you rotate this whole thing 90 degrees, you get the exact same scenario. And so there can't be any difference. The B is the same distance out the whole time. So we bring B out. The 2 pi r is the length. How many times does our current pierce the area defined by this loop? Well, I've tried to draw it in black here. This black is the area defined by our Amperian loop. And the current going around would pierce it right when it gets to here. So imagine these lines as current. It would pierce every time it went right there. Let me show you a visualization here. So, and you got to imagine every time the current went right to there. And then it comes back around right there. It pierces it, in fact, all of the end. This time, I get every single wire. Every wire's got a loop and hit right there. And then it loops around and it hits right there. So as many times as this is wound around, I'm going to actually just get it. So in our total n windings, if you had a toroid that had a total number of windings of n, well, that's just what goes here. So you'd get n times I, because you have n i's that get pierced through that area. You divide, you get B for a toroid or a torus as mu naught n times I over 2 pi r. So that's the toroid, not too bad. Those are the three that are like sort of the classic Ampere's law. The rest of these are going to be, let's say you looked into the guts of a current. That is to say, what if you, so this is a big wire, let's say a thick wire heading straight for us. This isn't a sphere, this is a cylindrical wire. And it's just coming straight toward us out of the screen. And it's coming from into the screen. And it's just coming right out. So this is within the wire and this is outside the wire. So we're zoomed way in now. Zoomed way into like inside one of these wires. So there's a whole bunch of examples like this. You could ask, what's the magnetic field inside the wire and what's the magnetic field outside the wire? If you're going to do these problems, you got to understand what current density is. So just like in Gauss's law or whatever, we define a charge density. With current, we define a current density. This right here is the current density, and we represent it with the letter J. J is the current density. You might think it's the current per volume, but it's not. Current pierces an area, so it's really the current per area. So however much current passes through some area, some cross-sectional area, that tells you what your current density is. Let's just say we had a solid wire with a uniform current passing through it and a uniform current density. So same current everywhere within here. It's not like there's more current per area here than there is over here, but it's the same amount of amps per meter squared. That's the unit of this current density. You could use Ampere's law to figure this out, so we can figure out what the magnetic field is inside of this wire and outside. So we do it just like before. We draw an Amperian loop. It's probably not surprising that the Amperian loop here is going to be a circle. First, let's go inside of the wire. So let's say our Amperian loop looks like this. Well, B is going to be uniform again along this loop. It has to be, it's just symmetrically impossible for it not to be. If you rotated this whole thing 180 degrees, it's the exact same scenario, so B can't be different here compared to there. So B gets to come out of the integral. You get integral dl. dl is 2 pi r. Left-hand side, no problem. How do we talk about the current enclosed? Well, I don't enclose all the current. My total current through this entire wire is I naught. I'm not going to get all the current. How much current am I going to get? Well, I have to make my own current density. So I'm going to say that the current density in this wire is the total current divided by, well, the total area, which is pi big R squared. This is the current density flowing through this particular wire that has I naught and R. So I take the total current, I divide by the total area, I craft my own current density, and now I have that. And if you want to find how much current, we'll just do this. If you want to find the current, multiply J by A. You can say the current in any one section will be the current density times the area of that little section. So now that I know this number, now that I know how many amps per meter squared, I could take that number and multiply by whatever area I want. I could take this little area right here, figure out what that height times width is, multiply by this J, and I'd get the tiny amount of current that passes through there. It'd be smaller than I naught, but if you added up all of these, you'd get I naught. Well, for our Amperian loop, the area that is enclosed by my Amperian loop is pi little r squared. So what I'm doing here is I'm taking J, this is my J that I crafted here, J, and I'm multiplying by my A within my Amperian loop, and I'll always have to multiply by mu naught. So this whole thing, JA, is the I enclosed. That would give you what the magnetic field is. You know, you'd always have to divide here. So I'm not dividing by the left-hand side, but you divide to get what the B is. That's what the B is inside of the wire. If R, little r, is less than big R being the radius of the wire. If I'm outside here, if my Amperian loop's out here and little r goes all the way out to here, Well, now I'm just enclosing all of the current. Like, you can't get more than all of the current. You might be like, can I multiply J, my J right here, by pi big R squared? You could, because that's like how much total area you got. But look, big R squared, pi would cancel big R squared, pi, and you just end up with I naught anyway. So if you're out here, you're enclosing all the current. There's no need to mess around with current density at all. You got all of it. You get B equals mu naught I over 2 pi R, which is, no surprise, the magnetic field from an infinite straight wire. So outside of a thick wire, you can treat it as an infinitely thin wire, as if all the current were at the center. You would never know out here if you couldn't actually feel where the wire went to. Okay, so that's that version. What if instead of giving you I naught, they gave you J naught? Let's say they spotted you, hey, I got another infinite long wire with a uniform current density, and I'm going to tell you what the current density J naught is. Instead of telling you what the I naught is, I tell you what the J naught is. Well, now you don't have to craft your own J naught. I got J naught. How do you find the current? Current, remember, is always J times A. It's the current density, current per area times area. And so I take my current density. If I'm inside the wire, I'm going to multiply by how much area I got right here, which is pi little r squared. I'd divide by 2 pi r. That means B would grow linearly. B would get bigger, bigger, bigger as you go further out, because you r squared over r gives you r. Then if I'm outside here, if my Amperian loop's out here, little r bigger than big R, well, I do have to just stop at big R. I have to multiply J naught by pi big R squared. This would be the total current in that wire. That's the total current flowing through this wire. And you just stop at that outer edge there. And then outside, B dies off like 1 over R, just like normal, because this R squared's just a constant. Outside the wire, B dies off like 1 over R, but inside the wire, B gets bigger and bigger linearly with R because of this relationship here. Okay, so how does this get harder? Maybe you get something tricky here. You get like a wire with a hole in it. So maybe there's just like a hole running down the center axial of this wire, and I give you what the total current is through this part here. What do you do now? Same deal. If your R is less than A, well, obviously you're not enclosing any current in here. So that's just 0. You got no current enclosed, so the B field is 0 in here, no magnetic field. What if your R is bigger than A, but less than B? Well, we got to craft our own current density. So here we go. Current density is the total current over the total area. The total area here would be pi B squared, but then I have to subtract the whole, minus pi A squared. So this right down here is all of this area right there. So that's my J that I just crafted. That's I naught over the total area. And then to get current, you always have to multiply J by A. Which A? Well, for my Amperian loop, I want just the I enclosed. Enclosed by what? Enclosed by my Amperian loop, which is right here. So this area right here is going to be pi R squared, but then I still have to subtract the whole, minus pi A squared. So this is a bit of a mess. This is like a nasty thing here. You can move the 2 pi over. There's not a whole lot to do. You can cancel pi's and clean it up a little bit, but it's kind of nasty in here. What if your R was outside of this whole thing? Well, if they spotted you I naught, well, guess what? You enclosed all of I naught. You're getting all of I naught now. You could just throw I naught in here, move on with your life. Outside, it's just like an infinite straight wire, mu naught I over 2 pi R. Would not never know the difference right there. Okay, so what if it's a hollow wire and they give you J naught? Well, you know what to do here. Inside the A, it's 0 because there's no current enclosed by an Amperian loop in here. If your R is greater than A but less than B, well, we got J naught. We don't have to craft our own J naught. We just say that the current we got is J times A. So that's J naught times just this area, which is what we used before, pi little r squared minus the whole, because it's not that area, pi A squared. And then if you're outside the whole thing, well, we didn't get I naught, so I can't just write I naught, but I can write J naught times the total area of this whole thing, which would be pi B squared minus pi A squared if I'm out here. Okay, now we get to the ones where it's not uniform current density. Theoretically, you could have any current density dependency you want, but 99% of the time, that current density is simply dependent on R, or at least the ones in the textbooks are. You rarely get a angular current dependency that's dependent on like what angle you're at, so you're just gonna have a radial dependence of some sort. What do you do with that? Well, okay, you're gonna have to be like, all right, imagine I have an infinitesimally small area right here, dA. Well, if I take the current density at that location right here, whatever that is, it might be different at different points. Current density times area would give me the current going through here, but that would just be an infinitesimal amount of current. How do I get all the current? Well, you integrate the whole thing. So you integrate both sides. You're going to get that the current is equal to integral J dA. That's what we're doing right here. So it's just the integral version of JA, but you got to do, if J is a variable, dependent on R, you have to integrate J with respect to dA. What the heck do you write for dA? Well, typically you have like cylindrical coordinates here, circular coordinates of some sort. You're not going to want dx dy, so you got to write dA in terms of like polar coordinates. How do you do that? Well, it's not too bad. I mean, just think about what A is for a circle. So the area of a circle is pi r squared. Let's say we took dA dr, like the derivative of A with respect to r. What would we get? Well, derivative of this whole thing with respect to r is going to be 2 pi r. Okay, great. Now move the dr over, and guess what? You get dA is equal to 2 pi r dr. That's what we got right here. So if you ever forget this, what dA is in cylindrical coordinates or polar coordinates, you could always get it. Just write down what the area of a circle is, take a derivative, move the dr over, and you get 2 pi r dr. That's what dA is, assuming you have no angular dependency. If professor throws the sink at you and you get a J that's dependent on like phi and theta, okay, you can't just do this. You got to actually write a three-dimensional, or go back to just straight up dr times r d theta and like mess around with stuff like that. But if there's no angular dependence, you can always just do it this way if it's just radial dependent. So that's what you're going to plug in. This whole thing goes in for dA. So see how this works. Let's say I gave you J as a function of r, and I wanted you to find the magnetic field inside here. So I draw a little Amperian loop. R is less than big R. So I'm going to say B times 2 pi r, bring the B out as always. I say it's uniform due to symmetry. I get B times 2 pi r because that's the length of my Amperian loop. I get mu naught I enclosed. So the I enclosed is this. I can't just do J times A. I got to do integral J dA. So I do integral J. Here's dA. I go from 0 to little r. Those are my limits because I just want the current in here. And you integrate. Let's say J was like r or something, r squared. Well, you'd combine it with this r here. You'd get r cubed. You do an integral. You get like r to the 4th over 4. You throw your limits in. It's not actually too bad at that point. What if you made your Amperian loop out here? You wanted to know what B was outside of the wire. No problem. Just stop your integral at big R. You can't be adding up any more current than all of the current. You got to stop all the way to here. Once you get to there, boom, integral's done. You got all the current. So this right here is an expression. Right here alone is an expression for the I total that's flowing through this wire. Sometimes problems just ask for that directly. They're like, hey, forget Ampere's law. Can you just tell me what the total current is through this wire? Well, this is it. Integral J dA through the entire A, like through the entire radius of this thing. And if you throw that in here for Ampere's law, that would give you the magnetic field if you divide by 2 pi r. How does this get harder? There could be a hole, but it's really not that much harder. 2 pi r for your length, you bring the B out. Inside of the hole, you're not going to have any magnetic field because the current enclosed is 0 inside here if you put an Amperian loop there. What if your Amperian loop is bigger than A but less than B? Same deal. You're going to integrate J dA. You're going to integrate from not 0 to r. You got to integrate from A to r so that you just pick up this area there. So make sure your limits go A to r, not 0 to r. And what if your Amperian loop was out here so that little r was bigger than B? Again, just stop your integral at the outside edge. So you're going to go from A all the way to B, and that's it. This would be an expression for the total current enclosed by your Amperian loop. And this would also be an expression for just the total current that's flowing through this entire wire with a hole in it. And then you divide by 2 pi r, and that gets you your magnetic field. So this was a sampling of most of the Ampere's law problems you might see out there. There's not a whole lot of difference here. This is a pretty good sampling. Hopefully these help you figure this out. I'll link to this worksheet in the video comments if you want a handy review guide. Good luck.